Hey everyone, sorry this video is getting up late. We had a really nasty storm come through last night and knocked power out all over town. So I wasn't able to record my video because we lost power before I was going to do it. Luckily I know someone who managed to keep power, so I am here. I'm going to try and get this recording done and get it up as quickly as possible for you guys. But because I'm doing it in the middle of the day, I have a helper here. So if you hear any random sounds, it's my youngest. She's hanging out on my lap and hopefully not going to disturb too much. Ironically, this week we're going to be doing Chapter 14, Weather Patterns and Severe Weather. I know Jamestown had some tornado warnings yesterday. Out here in north central Pennsylvania, we had 75-mile-per-hour winds. We had trees down all over the place. So some of the very recent weather events should tie in very nicely with this chapter for some of you. So let's get started. You hear meteorologists talk a lot about air masses. An air mass is a large body of moving air. It's typically 1,000 miles or more across and thousands of feet thick. The thing that makes an air mass like this unique is that it has very similar temperature and moisture content throughout the entire air mass. So no matter the altitude within the air mass or distance within it, it's going to be the same temperature. This temperature and moisture content in it is affected by the areas that mass moves through. So if an air mass moves through a very dry region, it's going to lose some of that moisture. A warm region is going to raise that temperature. And these air masses affect large portions of a continent. So we're not talking about like, a small thundercloud in an area. We're talking about these very significant in size bodies of air. And it may take several days for an air mass to pass completely through an area. There is an air mass over on the northern portion of Canada. So the Canadian air mass moving south in this image, and it shows that it modifies the weather of the areas it moves through. It's also affected by the climate conditions of the area it moves through. So you can see it's a very cold, dry air mass at negative 46 degrees Celsius. As it moves south, it starts to move through warmer regions, and it actually starts to raise the temperature of that air mass until it actually ends up above freezing by the time it reaches the southern portion of Mexico. Air masses can be classified in two different, they're classified by two different things, by a source region and by a source area surface. So source region, we have our polar or Arctic air masses. These are the higher latitudes and they're very cold. And our tropical air masses, these are low latitudes and they're warm. We also modify them by denoting their source area surface. So we have the continental, which form over land and are often dry, or the maritime, which form over water and are often humid. So there are four major air mass types on Earth. We have our CT, which are continental tropical. So these would be our dry, warm air masses. Our continental polar, which are our dry, cold air masses. Our maritime polar, which are our humid, cold air masses. And our maritime tropical, which are our humid, warm air masses. And that's my 2-year-old in the background. I apologize. I had to do this during the day to make sure you got it in time. Just a second. What, bud? Okay. So North America is primarily affected by the following air masses. I'm really sorry, guys. It's impacted by the continental polar, so you see up above Canada. This is the source of lake effect snows and brings the cooler air in the summer. We're also affected by the maritime tropical up through the Gulf of Mexico and off of Southern California. This is the source of hurricanes and tropical storms. And our maritime polar, you can see these come from the northern, eastern, and western coasts. These are precipitation to the west coast, cooler temperatures, and storms to the northeast. So here's our winter pattern, and here's our summer pattern. So you can see how these air masses move in relation to each other and change with the seasons. Okay, now today we're also going to cover our weather fronts. So fronts are sharp boundaries that separate air masses of different of different densities. In other words, air masses that have different temperatures and humidity. They are as large as air masses in lateral extent, so it's a line, it's a boundary, so it's like a linear boundary between them, so they can extend for thousands of miles along that boundary. But the boundary itself is very thin in extent, only about 9 to 150 miles wide, so it's extremely long but very narrow. The frontal types that develop are warm fronts. This is where a warm air mass advances into an area previously occupied by cooler air. Okay, sorry about that. Let's try this again. So here's an image of a warm front advancing where the warm air replaces cold air. You have a very gradual frontal slope because it's hard for the warm air to actually displace the colder air. The colder air wants to sink and stay down low, so it's very difficult for that warm air to move that cold air out of a region it's occupying because the warm air tends to stay above it as it is. Rains may be widespread and light to moderate, and it's a very slow rate of advance. Warm air fronts are very slow moving. And this just kind of gives you an example of the type of cloud formations you would get throughout a warm front and a warm air mass. A cold front advancing, there we go, is where cold air replaces warm air. They're much steeper than warm fronts because the cold, dense air can easily displace the warm air. It's coming in and it's moving under that warm air and pushing it up, which is much easier to do. Storms produced may be violent with very heavy rains, and it's typically followed by cold, dense, subsiding air and cooling conditions. So a lot of these very intense thunderstorms that we get are usually because of a cold front moving in. So here's just a video showing you the impacts of cold fronts and warm fronts. I will post that link on Blackboard. And then one showing just a really good description of weather maps and how warm fronts and cold fronts are explained. There's also what's called a stationary front. This is a non-moving boundary between two air masses, and this occurs when neither is strong enough to replace the other. I'm going to pause this video again. Sorry, guys. Okay, so a stationary front is when the airflow between the fronts are parallel to each other. So when a warm front or a cold front stops moving, it becomes stationary. Once this boundary resumes its forward motion, it becomes a warm front or a cold front again. So a stationary front is just where a front has lost the energy to displace another, and it remains in place. So that's where you can get extended thunderstorms or just extended cloudy conditions, because it's just kind of hanging out at this mix between the cold and warm fronts. It's typically depicted by an alternating of the cold front and warm front symbols, just to indicate that there is no movement along that at this point. And finally, we have what are called occluded fronts. This is a non-moving boundary between two air masses. Okay, so it's different than a stationary boundary. So this can happen when an active cold front overtakes a warm front from behind, creating a second wedge of uplifting air, and results in complex weather patterns. So as you can see in the image here, we have a warm front that's trying to displace cold air, but it is quickly being overtaken by another cold front from the behind. And as that cold front moves, it moves faster than that warm front does, creating this focal point where you have that warm front basically intersecting the Earth's surface with both cold fronts before that cold front forces that warm front up and overtakes it. So this is how you get an occluded front. Next are mid-latitude cyclones. This is basically, our region from Florida to Alaska, so our area. So the northern hemisphere, a cyclone is any counterclockwise spinning area of low pressure. We briefly touched on this in the last chapter. The air spins inward toward the center of the low pressure spiral. They're very easy to see on a satellite photo because it generates those clouds and stormy weather, giving you those really nice spiral arms out from it. Typically characterized by thunderstorms, tornadoes, hurricanes, and tropical storms all show cyclonic weather patterns. In the northern hemisphere, an anticyclone is clockwise spinning of high pressure. This is an environment that gives you very few clouds and extremely calm weather conditions because it's dispersing the energy outwards. The air spins out from an area of the high pressure. So this is just showing an example of movement of warm and cold fronts in a cyclonic region. So you can see the air is moving in a counterclockwise motion. And you've got your warm front coming in to try and displace a cold front. However, that cold front is essentially cycling back and retaking that warm front there, creating this occluded front right at the central point of your low pressure system. Okay, so using this map above, just give a weather description just like you would on the Weather Channel. So I really just want you to kind of go through this on your own, in your notebook or wherever you take notes on this, to kind of describe what's going on here. So thunderstorms. Thunderstorms form when warm, humid air rapidly rises. They typically generate lightning and thunder, gusty winds, heavy rain, and is characterized by strong up and down movements within thunderstorm clouds. They're very common along cold fronts of mid-latitude cyclones, so the U.S., and can be generated in isolation from a cold front. They can also be generated by tornadoes and hurricanes. They're common in the tropics because of the abundance of warm, humid air. And at any time, 2,000 thunderstorms are occurring across the earth. So this is just showing you thunderstorm formation. So when a cloud is in the cumulus stage, you know those like nice giant fluffy clouds. A strong updraft produces the moisture that condenses and builds the cloud. When this cloud then matures, it's marked by heavy precipitation. So that updraft exists side by side with downdrafts within that cloud cycle, and it continues to enlarge the cloud. So even as the cloud is precipitating out, you've still got an updraft bringing moisture in. And finally, when that updraft is exhausted or is moved away from, the precipitation becomes lighter because you don't have that continual introduction of moisture, and then stops. So this map is just showing the average number of days per year with thunderstorms. So what is the average number of days per year with thunderstorms in the Jamestown, Dunkirk area? And what percentage of the year is this? And you look at it, and what are the average number of days per year with thunderstorms in your area if you are not in the Jamestown, Dunkirk region? And why is there so many thunderstorms in Florida? Here's a video on how lightning works. This video is really, really cool. I actually did not know this before working on this chapter, so if you don't watch any other video this chapter, watch this one because it is a really awesome video. And I'll post the link. Okay, tornadoes, also known as twisters or cyclones, actually comes from the Spanish word tonar, which means to turn. So tornadoes are intense cyclonic storms of short duration. They last anywhere from a few minutes to a few hours. Their typical diameter at their base is anywhere from 500 to 2,000 feet, with a speed of, on average, 30 miles per hour. They take the form of a rotating column of air known as a vortex, and the wind speeds can vary from 65 to over 200 miles per hour. So the actual lateral displacement of a tornado is at about 30 miles per hour, but the wind speed of the air rotating within it can be over 200 miles per hour. There's a large pressure difference between the tornado and the surrounding air in high winds, which moves the debris and produces the destruction. They can occur in any month, but spring and summer have the greatest frequency in the U.S., and the average is about 770 per year in the U.S. So here this just shows how a tornado forms. So we've got the tornado. We have our winds. Okay. So here we've got basically two wind speeds. We have the stronger winds at higher altitude and weaker winds at lower altitude. And what happens is we get this rotation, horizontal rotation, vertical? Sorry. Very similar to how you'd see particle motion in the water. So we start to get these, like a hoop rolling across the ground kind of wind patterns. Yeah, horizontal vortex. once this wind pattern hits an updraft, this updraft actually tilts it and rotates it into a vertical column. And this vertical cylinder is established, is where tornadoes are established from. The tornadoes actually develop at the very base or the very bottom of this vertical cylinder of air. So when we're seeing a tornado, it's actually right down here. This air column, or this airflow that we're talking about, actually extends a couple kilometers in the air up through the atmosphere. So this is showing a tornado formation. So we've got faster winds up here. Sorry, she's still learning how to walk in. She fell and bumped her head. Okay, so we have our faster winds up here, 25 miles per hour. Our slower winds down here at 5. So you can see we start to get this rotating air because of the speed differential. Now, as it travels, it hits this updraft, which rotates it and creates this vertical air column, which is where we start to get that tornado air formation along with the precipitation. This is just a figure showing the occurrence of tornadoes across North America, across the U.S., and this is the average occurrence per 10,000 square miles. So you can see our peak tornado days typically right around June, but the number of tornadoes were actually peaking as soon as, or as early as April. So tornadoes are ranked in intensity just like hurricanes or earthquakes would be. So this is the tornado intensity scale. It's the Enhanced Fujita Intensity Scale, or the EF scale. So an EF rating of 0 is very light. You might get some damage to sidings or shingles. This is characterized by winds of about 65 to 85 miles per hour. So my region last night had winds of up around 75 miles per hour. So we were in an EF0 kind of storm. An EF1 is moderate with considerable roof damage. It can uproot trees and overturn single-wide homes. An EF2 up to 135 miles per hour. An EF3 are at 165. This is where you start to have hardwood trees actually losing their bark, and small portions of houses are completely destroyed. EF4 is up to 200. These are the ones we typically see. Residences, sections of schools, very well-built buildings are completely destroyed. Widespread damage with these. EF5s are over 200 miles per hour. They're extremely rare, and these are ones where you just see entire regions just completely decimated. Basically nothing left. Skyscrapers, mid-level buildings, everything is destroyed. Okay, next we're going to move on to hurricanes, which are known as typhoons in Asia. These are intense centers of low pressure that form over warm tropical oceans. Okay, most of the damage from these kind of storms are caused by the storm surge ahead of landfall, and then they're followed by inland flooding and tornadoes. They're characterized by winds that are sustained over 75 miles per hour. They have an average diameter of 375 miles, but can be as large as 900. And the energy that they get is actually from the heat that is liberated during the condensation of excessive water vapor in the air. So remember we talked about water vapor, and you reach saturated or absolute, saturated humidity. And once you reach that portion, you need to condense out. Well, as it condenses out, it expels the heat energy, which is what drives these environments. They typically form between 5 to 20 degrees latitude, except in the South Atlantic Ocean. So this just shows you the eye of a hurricane. I'm really sorry. Give me a second. Okay. And we have our hurricane eye, and then the eye wall, which surrounds the eye, and that is the most intense part of the storm. That's where most of the energy occurs. So here you have the eye, and you have air is actually sinking within the eye system. So the sinking air in the eye, it warms by the compression of the air around it. And the eye wall is the zone where the winds and the rain are most intense. So we've got our tropical moisture spiraling inward because of the low pressure, so it's moving in, right? And as it moves inward, it creates rain bands that pinwheel around the center. Then up top, we actually get an outflow of air because it prevents the convergent flow at the lower levels from filling in the storm. So we've got this inward movement at the lower levels, and then we've actually got an outflow of the air around the eye and up and out to prevent it from filling in lower down. So the eye wall is near the center and is identified by rising air with intense convective activity. It's a wall of cumulonimbus clouds and has the greatest wind speeds. Whereas the eye is at the very center, typically about 12 meters in diameter, 12 miles in diameter, identified by descending air which heats by compression as it descends. There's no precipitation, very calm winds, and it is the warmest part of the storm. So here's another cross-section view. So we've got our moist air moving in, and then our diverging airflow in the upper atmosphere, and then we have our air that's actually moving down through the eye and heating by compression as it moves downward. So hurricane intensity is characterized by the Saffir-Simpson hurricane scale. One more second. So this is just looking at the scale we use for hurricanes, and it's categorized 1 through 5. So Category 1 winds up to about 150 kilometers per hour, minimal damage, and it ranges all the way to a Category 5, which are greater than 250 mile per hour winds. These are the catastrophic, like the maximum destruction kind of storm events. So this is just showing in miles per hour. So a Category 1 can get up to 95 miles per hour, greater than 980 millibars of pressure. And a Category 5 greater than 155 miles per hour. You can see that there's a significant drop in the pressure for this type of hurricane. Additionally, tropical storms, or actually tropical cyclones, are classified in a different way. So a tropical depression moves at about 20 to 34 knots. Okay, so it's half to a third of the speed of a Category 1 hurricane. A tropical storm is 35 to 63 knots. So this is where it starts building intensity, but hasn't reached the hurricane level yet. And a hurricane is where it reaches speeds of 64 knots or greater. This is showing the tracking of Hurricane Allen from 1980. So we had our cyclone track, and it moved through the Gulf of Mexico right here, impacted land right on the eastern coast of Texas. This is where we had our maximum storm event. I'm really sorry, guys. You're not ever going to have another video with this many interruptions. Okay, let's see if we can finish this. So this just shows how the highest intensity of the storm impacted land right here, and kind of the rain and wind intensity as it moved through northern Mexico, southern Texas, before dispersing its energy here. And at this point, you're just getting your typical rain, cloudy weather at that point. So this is a video of Hurricane Allen. I will post this link. And that is the end of this chapter. Yay! Let me get through without my children ruining everything. A few of you have asked me about your papers. I have been hopefully getting to everyone's questions as quickly as possible. 3 pages, it is double-spaced. You do only require 2 scientific references. I would like to see 3, preferably though, but I'm only going to require 2. You're not going to get marked off if you only have 2. Most topics have been approved for anyone who had any questions about it. If I'm a little slow getting to your emails right now, it's because I'm basically trying to do everything off my cell phone, which doesn't have the best signal up here all the time. I have to kind of sit in my car and let it charge while I do this. So I'm going to try and get to everyone as quickly as possible. Hopefully we'll have power back sometime today or tomorrow. So by the time you see this video, it might not be an issue anymore. So I apologize for that. If you have any other questions, let me know.